Uh, the units we use to measure things are arrived at arbitrarily. We have a certain amount of water, say, and call that a liter. We take something, an object that weighs a certain amount, we call that weight or mass, gram. Set up an apparatus that generates a certain amount of energy, and we decide to measure that. Say that's 1 joule of energy. All these elements, all these measurements are arbitrary. The units are arbitrarily arrived at. So, to find a non-arbitrary measure, I decided to turn to the constants of nature, use nature's constants, and combine them in such ways that we get measures not based on arbitrary units, but determined by what we find occurring in nature. Now, this presentation could easily take over an hour, but because I'm trying to limit these videos to a few minutes each, I'm just going to mention the constants in nature that I've drawn upon in order to come up with this non-arbitrary system. I'm going to begin with big G, which is the gravitational constant, and then H, which stands for Planck's constant, and E, elementary charge, C, of course, the velocity of light, and I'll come back to A later, and then R is the gas constant. And instead of using grads or degrees or radians, we use fractions of a circle to give angles. Of course, K, Boltzmann's constant, and then we have mu sub b, which is the Bohr magnetron, and we have sigma, the Stefan-Boltzmann constant. And so we combine these things in certain ways to get measures of quantities, whatever quantities we happen to be interested in, we get a measure for those. Now, those quantities will turn out to be at an inconvenient scale. So here we have A, which stands for the fine structure constant, and that's a scalar, and it's approximately 1 over 137. So every factor of a fine structure constant, will bring down the magnitude of our measure, and every inverse factor of a will magnify it, will make it larger. Okay, so let's see. Okay, so I just wanted to take us through those.